Hello, I welcome you all on this new session on damped free vibration. Okay, already you know that damping it is the resistance to the vibrating body, and free vibration when the external force acts on any system. For example, in this simple pendulum, when the external force acts on it, the resulting vibration is called as the free vibration. Okay, in the damped free vibration, after a certain number of oscillations, it will stop. Okay, because of the resistance. Okay, when the external force acts on the system, it will oscillate between these two extreme positions. When there is no damping, then it will continuously oscillate between the two extreme positions. When there is resistance, after some oscillation, after a few number of oscillations, it will stops its oscillations. It will come to equilibrium positions. Okay, such a system is called as the damping system. Okay, let us study about the mass spring damping system. You can see the mass spring damping systems. Okay, when there is no vibrations, then the forces acts on it are the gravitational force, and to resist this gravitational force, there is spring force is there. Okay, at any time t, gravitational force magnitude is same as the spring force, but the directions are opposite. So we can say that mg is equal to minus k delta st. When the system is in in vibration, then the forces, this is the free body diagram, then the forces set up in the body are gravitational force, and to resist this gravitational force there is a spring force of magnitude k delta st. These are equal in magnitude but opposite in direction, and this is acceleration force, and to oppose this acceleration force there are spring forces and the damping forces. Spring force is kx and damping force is cx dot. Okay, so summing all the forces, mx double dot plus mg, it is in the downward direction, and to resist these forces there are damping force, spring force and the one more spring force. At any time t, always the magnitude of mg is equal to k delta st, so it get cancelled. So the remaining forces are mx double dot equal to minus kx minus cx dot. So it can be written as mx double dot plus cx dot plus kx is equal to 0. This is the equation of motion for the mass spring damping system. Okay, now we have assumed displacement function, that is x is equal to e raised to st. It is an exponential function. Why exponential function it is used here? It is a damping system. The displacement goes on decreasing with respect to time. Okay, so we need such a function which is either increasing or decreasing with respect to time. So exponential function, it decreases with respect to time. Okay, so then here we have the equation of motion mx double dot plus cx dot plus kx is equal to 0. Here we have the accelerating component x double dot. X dot is the velocity component and x is the displacement component. Okay, by this assumed function, let us find what is the velocity component and accelerating component. Differentiating this displaced component, we have s e raised to st. This is the velocity component, and again differentiating this velocity component, we have x double dot. This is the accelerating component, that is s square e raised to st. Substituting this x dot and x double dot, displacement, velocity and x double dot in this equation, okay, we have ms square e raised to st plus cs e raised to st plus k e raised to st. As e raised to st, it is common in all the terms, it is taken outside, so it is ms square plus cs plus k equal to 0. Okay, so when it is simplified, we have ms square plus cs equal to plus k equal to 0. This is the quadratic equation. We already know how to find the roots for the quadratic equation, that is by the equation minus b plus or minus square root of b square minus 4ac by 2a. In the similar fashion, the roots are written here. So the roots are s1 and s2 are minus c by 2m plus or minus square root of c by 2m whole square minus k by m. Okay, see here, the solution, it depends upon this quantity, whether it is positive value, negative value or 0. Okay, when this c by 2m whole square it is more than k by m, then the quantity is positive. If c by 2m whole square if it is equal to k by m, then it is 0. If c by 2m whole square it is less than k by m, then it is negative value. Okay, when this quantity is equal to 0, when c by 2m whole square minus k by m is equal to 0, then c by 2m whole square is equal to k by m. Okay, then the damping coefficient is equal to 2m into square root of k by m, that is 2m omega n. When c by 2m whole square is equal to km, then the damping coefficient is called as the critical damping coefficient. Okay, that is 2m omega n. Okay, then what is the type of system we are finding by this critical damping coefficient? Okay, the ratio of actual damping coefficient to the critical damping coefficient is called as the damping ratio. Okay, the ratio of actual damping coefficient to the critical damping coefficient. What is critical damping coefficient? When c by 2m whole square is equal to k by m, then what is this c value? That c value is, that damping coefficient value is called as the critical damping coefficient. Okay, see here S12, the same equation taken here, the same roots. C by 2m, okay, it is written in terms of zeta. C by 2m, it can also be defined as c by cc. C by cc, it is nothing but damping ratio, into cc by 2m. This cc get cancelled, so again it is c by 2m. What is c by cc? It is zeta. Cc is equal to 2m omega n. Cc is equal to, see here, cc is equal to 2m omega n. Okay, so this c by 2m, it is nothing but zeta omega n. Okay, zeta omega n. C by 2m, it is zeta omega n. Substituted c, this value also, zeta by omega n, zeta omega n. K by m, it is nothing but omega n square. Omega n, omega n, omega n. It is common in all the terms, so it is taken outside. So this is the roots of the equation. Okay, all the solution, it depends upon the zeta value, whether it is positive, negative or 0. Okay, the solution for the differential equation, as it has two roots, we have considered two roots. The most general solution for the equation is x is equal to a1 e raised to s1t plus a2 e raised to s2t, where s1 and s2 are the roots. See here, s1, s2. For s1 you consider positive value, s2 consider negative value. a1 and a2 are the constants. Just substitute the value of s1 and s2 here. Okay, this is the most general solution for any system. Okay, depending upon the value of zeta, okay, the roots are, if zeta value is more than 1, then the roots are real and negative. Okay, such a system is called as the over-damped system. Okay, in that case c value will be more than cc. Similarly, when zeta is equal to z1, the roots are real and equal. Okay, then it is called as the critical damping system. Okay, when c is equal to cc. Similarly, when zeta value is less than 1, the roots are imaginary. Okay, when c value is less than cc. Okay, depending upon the zeta value, the system get changes. If zeta is more than 1, that it is over-damped system. If zeta is 1, then it is critical damped system. Then zeta is less than 1, then it is under-damped system. Okay. Okay, in the next video we will see the response of the system for over-damped system, critical damped system and under-damped system. Okay, thank you.